While all normal distributions exhibit the same properties, such as symmetry or the 68, 95, 99.7 rule, not all normal distributions have the same mean and standard deviation. So if I need to compare two normal distributions, how can I do that? Well, we're going to relate them all to something called the standard normal distribution. The standard normal distribution has a mean of 0 and a standard deviation of 1. Notice the notation is a little bit different here. For the mean, we're using the Greek letter mu. It's a lowercase mu, whereas previously we were using x bar. And for the standard deviation, we're using the lowercase Greek letter sigma, where previously we had been using an s. So why the change in notation? It's a very subtle change. The mean of a sample is denoted x bar, while the mean of a population is denoted with the mu. Similarly, the standard deviation of a sample is denoted with an s, while the standard deviation of a population is denoted sigma. So if you'll recall, the population is the entire group under study, and a sample, if it's representative and random, can be used to infer conclusions about the population. So when we're describing the entire population, we use the Greek letter mu for the average or the mean, and we use the Greek letter sigma for the standard deviation. So aside from that subtle change in notation, we want to recognize if we're dealing with the standard normal distribution, then the average is 0 and the standard deviation is 1. Let's see what that looks like on a graph. So we're still dealing with an ordinary bell curve, a normal distribution. So we can draw it something like this, where the data points are spread out on the horizontal axis and the vertical axis gives us the frequency. For a standard normal distribution, the mean, which we're now going to call mu, is 0. Then each unit that we measure above the mean and below the mean will be in multiples of 1. So it makes the distribution very easy to read. So 1 standard deviation above and below the mean, 2 standard deviations above and below the mean are very easy to denote. So positive simply means we're above the mean, and negative means we are below the mean. Now, we can have different looking standard deviation, normal distributions. For example, we may have one that's really tightly packed around the mean, looks like a tall and skinny bell curve, whereas we can have one that's more generally distributed. You've got a gentler looking curve, a flatter hill, if you would. All of these are normal distributions, but we can convert each of these into what we call the standard normal distribution to figure out how those relate to each other. One way that you might be able to understand what's going on here is with currency. As Americans, we measure our currency in dollars. So if we go to a different country, like Mexico, for example, uses pesos, or Israel, for example, uses shekels, in order to figure out how do I convert shekels to pesos or vice versa, we're going to relate everything to what is most familiar to us, that is dollars. And that's what the standard normal distribution does. It will take any normal distribution and convert it into this one standard unit of measure. To do this, we're going to need something called a z-score. A z-score describes how many standard deviations above or below the mean a data point lies. So where we normally use the variable x to represent a data point in a normal distribution, we use the variable z to represent a data point in the standard normal distribution. So to convert from one to the other, we're going to take the data point from our normal distribution, which we call x. We're going to subtract the mean, which we call mu, and we're going to divide by the standard deviation, which we call sigma. So notice x minus mu, if I have some point x over here, and I find that difference, x minus the standard deviation, x bar, or let me go ahead and write it mu so we get used to that. X minus mu, that's the difference or the distance between those 2 points. Then I'm going to divide by the standard deviation, and that's going to tell me where does that point, which we previously called X, where does that point lie on the standard normal distribution? And that's what we call a z-score. Now let's do an example to be sure to clarify that information. The gestation period for a horse is normally distributed with a mean of 336 and a standard deviation of 3 days. So if I'm studying horses and looking to predict when will the young horses be born, we're going to understand they're normally distributed amongst the horse population. So the mean, which we're going to call mu, is 336 days, and the standard deviation, which we can call sigma, is 3 days. Now, we want to find the z-score for 342 days. So the z-score is going to be our data point, that's 342, minus the mean divided by the standard deviation. So we're going to take 342, we're going to subtract 336, and we're going to divide by the standard deviation of 3. So we end up with 6 divided by 3, or 2. So this means that this 342 is 2 standard deviations above the mean. Now, it always helps to understand what's going on if we actually look at a picture. So we're looking at a normal distribution that is centered at 336, the mean. Now, if the standard deviation is 3 days, then 1 standard deviation above the mean would be 339, and then another 3 units would give us 342, 345. Okay, so I'm just measuring these tick marks using units of 3. And we've got our bell curve, something like this. So on example A, we were looking at 342 days. So notice here's 342 days. When we found the z-score, we got a z-score of 2. 2 simply means that the data point we were considering is 2 standard deviations above the mean. Let's try another example. Let's find the z-score for 333 days. Now remember, the z-score is the data point minus the mean divided by the standard deviation. So we're going to take our data point, 333 days. We're going to subtract the mean, that's given to be 336, and we're going to divide by the standard deviation of 3. Notice in this case we get a negative 3 on top and a 3 on the bottom. So our standard deviation, or our z-score, is negative 1. How do we interpret that z-score? Well, if we look at the graph, we're working with 333 days. So here's where 333 days lands on the graph. This means the z-score is negative 1 because notice we are 1 unit or 1 standard deviation below the mean. So if we were to convert this normal distribution into the standard normal distribution, then we understand that we're working with a data point for example A that was 2 standard deviations above the mean, and a data point for example B that was 1 standard deviation below the mean. So the z-score simply counts how many standard deviations above or below the mean that particular data point happens to lie. Let's try another example. Now, as I mentioned previously, if we convert a normal distribution into the standard normal distribution, then we'll be able to compare 2 different normal distributions, and that's what this example is really about. A standardized grammar test is normally distributed with a mean of 84 and a standard deviation of 10. This is denoted N for normal distribution. And notice the first number here is the mean and the second number is the standard deviation. So if it's normally distributed, we have the mean listed first and the standard deviation listed second. A standardized math test is normally distributed with a mean of 300 and a standard deviation of 30. This is denoted in 330. Now, a student scored a 72 on the grammar test and a 255 on the math test. So which test had better results? Were they stronger in grammar or stronger in math? Now keep in mind these are standardized tests, so they're not graded on 100-point scales like our normal tests in our class, for example. They're scored on different scales. So we want to know, how do we compare these two tests? Well, we're going to convert them both to the standard normal distribution. So let's begin with the grammar test. First of all, we're going to recognize that the grammar test is normally distributed with a mean of 84 and a standard deviation of 10. Again, the mean mu comes first and the standard deviation sigma comes second. So this particular student made a 72 on the grammar test. So the score on the grammar test was a 72. We want to know, where does that score stand relative to the distribution, relative to the other students that took the test, and in particular relative to the mean. So we need to find the z-score for this test. Remember, the z-score is the data point minus the mean divided by the standard deviation. So this data point is 72. We're going to subtract the mean of 84 and we're going to divide by the standard deviation of 10. Now 72 minus 84 gives us negative 12 divided by 10, or negative 1.2. So that means that this particular student was 1.2 standard deviations below the mean. Remember, the mean describes how the measure of central tendency, where most of the test scores tended towards. This student was a little bit below average, 1.2 standard deviations below the mean. Now let's do the same thing for the math test. The math test, we are told, is normally distributed with a mean of 300 and a standard deviation of 30. So two very different grading scales. This student made a 255 on the math test. So we're going to find the z-score for the math test. We're going to take the score, 255, minus the mean of 300 and divide by the standard deviation of 30. So 255 minus 300 gives us negative 45, and we're going to divide that by 30. So we end up with negative 1.5. Again, this student is below average, but was further away from the mean on the math test than on the grammar test. So it looks like the student performed better on the grammar test. So in conclusion, we can say the student did better on the grammar test. And remember, that is relative to the population taking the test. So everything is measured against all of the different scores for that test. Now, what's interesting about this example, after our chapter in logic, we know that grammar and math are very much related. We learned how to take something written in English and convert it into symbolic form and apply mathematical rules to that symbolic form to judge the validity of certain statements. So grammar and math are very much the same. So we can't really say I'm an English person or I'm a math person, because those two subjects are definitely related. But as far as this example goes, we took two different normal distributions. We converted them both to the standard normal distribution, and we were able to compare z-scores to figure out which test the student did better on.